And so what Oza brought in was that these Galileo-NIMS observations apparently give a larger range in the grain size, and this particular calculation is relatively sensitive to grain size. And so we can then estimate essentially the number fraction of O2 relative to water, and of course, so water is the ice, in the very, very near surface, so photon depth type, photon penetration depth, length scales. And you see that there's quite a variation, somewhere between 0.3 and 12% of the solid, or of the material is O2. And so we already here we get a larger range than previous data just by incorporating like a larger range of ice grain sizes that are suggested by this Galileo-NIMS data. Now, so the important part here is, so in this second sketch here, what you see is essentially the top of the ice shell. And you see that at the very top, I've drawn this granular regolith. And this regolith is generated by something called impact gardening. So that's the small impacts of micrometeorites that kind of just stir it up. And this is something that people apparently discovered on the moon, where essentially this continuous bombardment just slowly degrades the surface and generates some sort of very fine sediment. And people believe that the same thing happens on Europa. And one question now is, it's generally assumed that, because when a little impact here hits these grains get all mixed around, that even if, this reaction here that happens probably only over a few photon path lengths, that the stirring of this regolith will mix in, will turn over this material, right? And so as such, generally people assume that this porous regolith is, has the same oxygen abundance as, as what you see on the surface. And so there's a question as to how thick this regolith is. And the regolith, of course, grows with surface age. Okay, so the older it gets, the deeper the regolith gets. And there's a form, there's like literally, the way this works is there's like 4 or 5 measurements on the moon. I think 4, and they discard the one that's an outlier. And then people fit a line to it, and it's, it's not an excellent fit. And ever since, people seem to have just taken that fit and applied it with religious fervor. So previous estimates were based on a particular set of numbers by Cooper et al. And, you have to think this is not the moon, right? It's not silicates. So, I feel one ought to allow for some variation in these parameters, since I don't think they're fixed. Even if you just fit the moon data, you would strictly, if you did some uncertainty analysis, you'd have to allow for a whole range of parameters. So I just, by gut feeling, decided to give myself a factor of 5 in these parameters. And then we end up with regolith between, 20 centimeters and 40 meters. Now, I've learned from feedback that people's intuition tells them that you cannot have a 40-meter regolith. It's not entirely clear to me where the intuition comes from, because we haven't really observed these regoliths anywhere else except in the moon. It must be from how big people think these impacts are, and I guess how far people think they can penetrate. My question then is, what gives an upper limit to how big these micrometeorite impacts are, especially if there's no atmosphere? So anyway, so we've decided to give ourselves a slightly larger range here. So this regolith is somewhere between tens of centimeters to tens of meters. And then we can combine the two together with some assumption of porosity, and we can calculate the total oxygen, or estimate the total oxygen in Europa's regolith. And we come up with numbers somewhere between 10 to the 14 and 10 to the 18 moles over the whole surface, right? And so just in summary, so we have somewhere between 0.3 and 12% of oxygen per water. We assume that we have regolith depth somewhere between tens of centimeters to tens of meters. Interestingly, the astronomers think that the porosity of the surface is somewhere around 90%, but I have decided that that's where I have a physical intuition. So I work on porous media, and the only porous medium that has 90% porosity that I know is like a volcanic glass, like scoria. So I have trouble imagining the surface of Europa like that. So we're going to assume porosities in a more reasonable value between 30 and 60%. And if we do this, as I said, we come up with a total estimate of the moles of oxygen in Europa, somewhere 10 to the 14, 10 to the 18. Okay, so that's the budget we have available. And now, and that's a big if. So when this is really only our estimate for what's in this regolith, right? And this regolith is generated only by impact gardening. Now, other people, and I didn't know this in the beginning, so if there's any deposition at all from cryovolcanism, from plumes, anything at all that's sediments on top of this, then of course you're going to bury these oxidants much deeper, right? And there's definitely papers out there by Greenberg and others that even assume the entire ice shell is oxygenated, right? So if this, if you continuously deposit, right, then you continuously bury it deeper and deeper, and after some time you're going to end up at the bottom of your ice shell. So there's people that are very, very adamant that there's only a thin regolith and only that is oxygenated. And on the other extreme, there's people that think the entire ice shell is oxygenated. And I'm sort of somewhere in between. I think that there's probably some form of deposition. And so I think that there's ice underneath this regolith that used to be regolith that has now been buried by stuff that's been put on top that is also oxygenated, okay? And that's important because if the oxidants are really only in the top few tens of centimeters, it's going to be really hard to get them down, okay? But that's something that all the different processes will share, right? If you really need to, get in contact with the very tippy top of this ice shell, then it's just that much harder, right? And so, of course, if the ice beneath this regolith has oxygen, is oxygenated, then of course this, is a lower bound, and you could be if you say had 100 meters, now you're 2 orders of magnitude more oxygen. You're a kilometer, 3 orders of magnitude, right? So this should be seen as sort of a lower bound, both because this is the thinnest possible oxygenated layer, and it's only oxygen, so there's other oxidants around. All right. Now we've established that we have oxidants, or we've followed through with the calculations that other people have done. And now we need to think, okay, how can we get these oxidants down through the ice? And that's, so I'm a dynamics person, and so that's fun for me to think about. All right, so here are, as far as I can tell, the processes that have been proposed. And so Greenberg et al. Has essentially, he's got this great paper that's full of pencil drawings like this. One day I want to be famous enough to get away with that. But he makes this point, there's all sorts of processes from tectonic thickening to, cryovolcanism to various kinds of plumes and the resultant deposition that will likely bury, that will add stuff to the top of the surface. And so some sort of resurfacing will bury the oxidants. If you continue, eventually you go all the way down, right? So that's one process. People don't seem to talk about that very much, but I think, so it's probably not, it's clearly not a very fast process if you need to rely on this to move the oxidants all the way through the ice, right? But it's certainly a good way of getting the oxidants deeper into the ice. And actually and so I guess whether there are processes that would bury the surface and resurface will depend on whether these preliminary observations of plumes on Europa turn out to be substantiated, and hopefully with Europa Clipper we'll get a clearer picture of this. So the other proposed mechanism, right, to connect the underlying ocean with the surface, of course, is to breach the ice shell with an impact. And so Rona Cox and one of her grad students have worked on this, and this hasn't, I guess, received a lot of attention, partly because maybe you need very large impacts to penetrate the ice shell, and those don't come along very often. And there's essentially there's no impact structures on the surface of Europa that look like they would have penetrated the ice shell. Although some people argue that maybe chaos terrains could be penetrating impacts, but that doesn't seem to be a popular idea. We're actually, so that's kind of, it's hard to imagine that you could sustain an oxygenated ocean with, the kind of very rare penetrating impacts that come along. And so my understanding is that most of the attention was for a long time focused on subduction. So where somehow the ice crust gets subducted or subsumed into the ice, and then there's convection going on, and eventually you mix the oxidants into the ice. Again, if your oxidants sit only in the top 10 centimeters, right, they're going to actually just get scraped off here. So no matter what the process is, it helps to have them penetrate, have the ice be oxygenated deeper down. And then finally, actually very early on, Christophe Sautin and collaborators, already suggested, of course, that there is probably melting going on, and some of this melt is draining, and that's, of course, what we're following up on. Now, let's just briefly look at this. So, so really, it's somewhere between subduction and brine drainage, and we're actually currently revisiting the impacts. And if there's time, I can talk about that briefly. So there's a famous or well-cited paper by Simon Kattenhorn and Proctor, where they've identified somewhere here in this little dashed area, they've found a region where you can make a very good geological argument that something has been shoved on top of something else. And so that's fantastic. That's really great detective work. But the fact is that this is only a very small area, right? So yes, we found something being subducted somewhere, but it's clearly not something that jumps out as you as a primary mechanism that's operating on Europa's ice shell. So this can certainly contribute, but again, if you needed an ocean to be oxygenated by this single, 2,000 to 20,000 square kilometers subducted slab, that's going to be hard. Now, if we get better data, we may find better, in particular, better coverage of all of Europa's surface. We might find a few other of those places, but again, they're not very abundant. And so this is why we decided to look at this idea of brine drainage. And we're not the first ones to think about brines percolating through Europa's ice shell. Gaidas and Nimmo had an early Nature paper that is very sort of back of the envelope, though. Then, of course, there's the Sautin paper that I just showed you. But the person that really put some, let's say, physics to this is Klara Kolosova, and this figure on the left here is one of her figures. Now, she assumes that there's something that forms melt. So what are we looking at? We're looking at depth through the ice shell, so 30-kilometer ice shell. And this is the porosity, and we assume all the porosity is filled with some sort of brine or melt. And she assumes some initial condition where the brine forms near the surface, and then she shows how this brine essentially percolates down through the ice. And one of the things that you see here is you see these Gaussian-shaped bumps, and these are solitary waves that form. They naturally arise in this kind of system of equations. And so that's a feature that's very common to melt migration, and you'll see that in our work as well. There's other people, and Noah Hammond has also worked on this. The thing that caught my eye here is that, so none of these papers, except actually for one LPSC abstract by Amy Barr, mention brine as a pathway for oxidant transport. They're just sort of interested in whether you can sustain brines in the near surface. And one thing that's interesting is clearly here the brine drains out of the ice shell on a time scale of tens of thousands of years. There's an interesting question is whether they would actually transport oxidants. And the reason that I say this is that there is actually a long-standing, melt migration, of course, is a subject outside of icy ocean moons, and it's mostly been developed for, what's in the chat? It's mostly been developed, of course, for melt migration in the Earth's interior. And there, people have actually shown that it's very hard to transport geochemical signatures with these porosity waves that migrate down. And so here's an analytic solution. This is based on the work of Frank Richter back in the 80s, where the black Gaussian looking, it's really a cinch type hump here. That's our porosity, solitary porosity wave. And you can see that it's migrating with a fixed phase velocity. Now in the Earth, this is for the Earth, so the melt is buoyant, so it would migrate upward. And then in color, you see two different tracers. One, the green one is perfectly conservative, so it doesn't partition into the solid at all. And the blue one is a sort of a more realistic tracer that whatever it is that you're looking at also partitions a little bit into the solid. And you can see that the partitioning tracer is left behind in this porosity wave very quickly. But even the perfectly conservative tracer is left behind. And so, so it's, you know, in the Earth, sort of the geochemists have lost interest in this, because if it doesn't transport geochemical signatures, then you can't detect it in the geochemistry of the basalts that erupt to the surface. And so, you know, coming from that background, I was curious whether the kind of porosity waves that Clara here has simulated, whether they would actually transport any oxidants or not. And the answer is yes. And the main answer is that this is an enormous distance. You need to migrate these porosity waves an enormous distance to lose all of the tracer that they initially had. That's part of the answer. And the other part is that these are in 1D, and in higher dimensions, the physics change. So, but before we can, you know, have the luxury of thinking about the transport of oxidants within these sort of porosity waves, you know, we need to think, are there any liquids or brines or melts that are close to the surface? And so on Europa's surface, there are multiple surface of, you know, observations that people have interpreted to indicate near surface melting. So the least controversial probably is if you have an impact crater, right? The impact can melt the ice, and that will generate potentially significant volumes of ice, sorry, of melt close to the surface. And it's an interesting question, what happens to those? And we're just starting to investigate this. Another one are these very particular so-called chaotic or chaos terrains that, you know, at least to me, certainly do look like some sort of broken up ice shell with some sort of cruddy, mushy, frozen stuff in between. And then there's all sorts of other smaller features. And in pretty much all of them, partial melting near the surface has been invoked as a mechanism to form these. And you can, well, actually, I'm not sure if this is true, but if the if the grayish brownish stuff here is actually oxidants, then you see that they would nicely collocate. Although I'm not positive that's not just coloring. Okay, so we're going to focus of all of these. So the impacts are its own story. So we're going to focus on melts beneath these potential chaos terrains, and the reason is that they're quite abundant. So this is a map by Senskedal of Europa's geology, and everything that is in some shade of green is in some way chaos. Now, I'm pretty sure that not all of this green is as nice, you know, as characteristic looking chaos terrain as this one shown here, but even if only half of the green stuff would look like this, then there's a significant portion of Europa's surface that seems to be affected by whatever the mechanism is that forms chaos terrains. And you can compare it, for example, to the yellow areas, right, which is what's the part of Europa's surface that's affected by impacts. And you see that certainly impacts affect a lot less of the surface. And as such, this is my daycare pickup. Just a second here. Sorry. Okay. Yeah. So we'll focus on these chaos terrains, and the problem with this approach is that we don't understand how chaos terrains form, and you know, and so you can get into a lot of discussions on what these chaos terrains look like exactly. There's a review by Collins and Nimmo that has accumulated the different kind, I think up to 9 different models of how chaos terrains might form. And I've selected just 4 here for the purpose. But no matter what the model is, they always involve here these white, gray dotted areas, right? And those are partially molten regions, right? So most authors that, you know, speculate about how these chaos terrains form invoke melting very near the surface. And you can see that these, you know, there's these regions that look like the broken up ice plates, right? And then there's sort of this cruddy stuff in between. And clearly, I mean, these images suggest that this cruddy stuff in between might actually be some sort of melt or mush that has come to the surface. And for example, we see enrichment of sodium over these chaotic terrains, indicating that some sort of salty brine may have come to the surface. So, and hence, we're simply going to assume, right? So our purpose is not to try and understand how chaos terrains form, but our purpose is to say, well, most of these models seem to assume that we form rather large volumes of melt in the very near surface. And our quest is now what happens to these, okay? Now, just the main ingredient that people invoke to form this near surface melting is some sort of eutectic melting point depression. So if you add, right, water and salt, sorry, ice and salt, they don't form a solid solution. So you have a eutectic phase behavior, and you can depress the melting point of the mixture by, in this case, some 20 odd degrees. And there's other salts that will depress it even further. And so typically people invoke the presence of salts to induce melting near the very, very cold European surface. So here's an example. So I'm, unlike, so Natalie Wolfenbarger has done much more careful calculations of this, but I've made myself a linearized sodium water phase diagram, because that allows me to everything analytically. And strictly this liquidous surface here is slightly curved, but I've just linearized it. And what you can then see here is you can see essentially the phase assemblage as a function of temperature. So below the eutectic temperature here, which is dashed, you have ice and salt, so two different solid phases. And then you form, at the eutectic temperature, you form brine. And then as you increase the temperature, you increase the amount of brine. And then here you hit what's called the liquidus, and above that, everything is liquid, and that it's a temperature that is lower than the melting point of ice, the pure ice. Now, one problem with this, just invoking salts, is that the amount of, right, so you need to melt at a low temperature, right? And the amount of melting that you get at a low temperature is linearly proportional to the amount of salt that you have, right? And nobody's arguing that Europa's crust has like 30% by weight salt in it, right? Everybody's just talking about impurities. So if you have very small amounts of salt present, then you will only get very small amounts of melting. And that's what's shown down here in the bottom diagram, that simply shows the volume fraction of brine as a function of temperature for different weight percent of salt present, right? So if you only have a smidgen of salt, so you're somewhere over here, then essentially what you get is you get a smidgen of melting at the eutectic point, and then you get nothing for a very long time. And essentially only once you approach the melting point of pure ice is when you see the melting pick up. Now, we're probably somewhere in a 5% range. So there's definitely some melting that happens, but then even then you still need the latent heat, right? So to generate that melt. And that's, okay, so an interesting point is when people try to think about how these chaos terrains form, they invoke the topography, because that's one of the few things that we think we know about chaos terrains. And so there's one thing is that some chaos terrains seem to be elevated above the surroundings, and then there's arguments whether these blocks inside the chaos terrains are elevated relative to the mushy stuff in between or not. And in particular, the fact that these chaos terrains are elevated has been invoked as a sign that melts don't drain. Now, talking to the people that do stereo image topography, it seems that there's some doubt whether they're actually elevated or not. The data apparently is just not good enough to really tell this, and that's something that should be resolved. I just want to, before we get deeper into this, I don't want to get people distracted thinking, well, the brine can't drain because otherwise we would have a depression. So now imagine that we have a salt poor convecting ice overlain by some salt rich upper ice, right? And then we have some process that causes this near surface melting, where essentially the salt rich ice begins to melt. Now, Brittany Schmidt and Don Blankenship have made a very nice argument that the sort of variation in overburden would drive the melt towards the center of this chaos terrain, which would cause a bump that you can kind of see here. But now's the question, what happens now, right? And so I would argue, right, so this, obviously all the salt goes into the brine. As soon as there's brine, all the salt petitions into the brine. If you were to refreeze all of that water in the center, you get a volume increase, because when you freeze things, the volume increase. When you freeze water, the volume increases. But you also have now all the salt in the middle. And so I agree that initially we'd certainly get an elevation in the surface. But in the long term, right, you've taken dense stuff, the salts, and you've concentrated them in the center here. And of course, what I've drawn here is ridiculously exaggerated. But I do believe that if you accumulate dense salts in the center of a chaotic terrain, in the long term, you would expect subsidence, simply because the crust is thicker, and the bottom of the ice is just going to adjust due to the melting point of the ice. If instead the salt drains, you remove the dense stuff from the near surface ice, and as such, the crust or the ice shell section here would have a lower density than it has far away from the chaos. And so at least that would, as a tendency, likely give you uplift. Now, the big question is, whether these are measurable effects or not. But people invoke it one way, so you can also invoke it the other way. So let's just, the other issue with chaos formation is the energetics, right? And so this is what everybody seems to struggle with, is where the energy comes from to generate near surface melting. So here was an attempt by Nimmo and Giese to sort of generate near surface melting. And essentially in their calculation here, you can't do it. You can see that they also assume salty ice, and they depress the melting point here, and then they place a diap here, and they show that, you don't exceed the melting point here, except at the very, very bottom of this salty layer. And clearly all the models that I've shown you seem to assume that melting happens essentially almost all the way to the surface. Now, there's some things that are wrong with this particular calculation. This is, if you had an actual upwelling, that would be sustained, so it wouldn't. So this is just a one-time delivery of warm material. But if you had an actual upwelling, that would continuously, have an elevated heat flow. We can also argue about this particular temperature profile. So you'll see in a second that the temperature is much closer to the melting point over most of the convecting ice. But nonetheless, it's very hard. You need a lot of energy to warm up the ice. And even if you have salts present, you still need the latent heat to generate vast amounts of melting near the surface. So the question is now, where can this energy come from? And again, this is not the problem we've wanted to solve, but this is where the discussion always goes. So I think there's different options here, right? So one that we investigated and unfortunately sort of excluded is, we had this idea that maybe if there's gas class rates that destabilize, you could somehow generate a lot of buoyancy at least and thin the conductive lid. So it turns out the gas class rates are stable throughout most of the ice shell. Krista Soderlund had a nice paper where she showed that, just the ocean dynamics can increase the heat flux in certain areas near the equator by, I believe, 50% or something like that. It's quite significantly, so that's helpful. My personal favorite that I don't think anybody has explored, and that's certainly on my list of things I would like to do, is that if you partially melt ice, then the attenuation, in other words, and with that the tidal heating increases. So it's this odd phenomenon where, although the viscosity drops when you melt, because you now have two phases that you can move against each other, you can suddenly increase. Unfortunately, this figure is terrible, but terrible resolution. But the colorful lines are the attenuation with melting, and the gray lines are without. So you see that you get potentially an order of magnitude more dissipation, and this would have a really nice positive feedback where, if something like maybe Krista's localized warming here generates a little bit of partial melt, this would be a positive feedback that could really maybe help you generate substantial amounts of melting near the surface. And if everything else fails, then, well, then there's always that tidal heating is really, really complicated. And so here's a nice diagram of the heat production rate by tidal heating for an IO Europa system. And you can see that it oscillates due to resonances. And recently we had a speaker that argued for Enceladus that we've dramatically underestimated the amount of tidal heating due to not understanding the internal dynamics of Saturn properly. And something similar could potentially apply at Europa as well. So, we're still looking for the source of energy to form these chaos terrains, but some combination of these factors, I believe, could help achieve it. So with that, we can finally move on to the things that we've actually been looking at. So if we want to bring oxidants down by draining the water, that's the melt that's underneath the chaos terrain, well, then first we need to have near surface melting, right? And I've just talked about this. Secondly, we need to mix the oxidant in the brine, right? And here there's two options, right? Either, the philosopher goes, the mountain comes to the philosopher, or the philosopher has to go to the mountain. So either you need to get the brine, the partial melt, onto the surface, as is potentially suggested by some of these sodium enrichments that you see, and maybe by some of the let's say, this mottled topography texture, or you simply need to have the oxidants buried more deeply in the ice. And that's my favorite. No matter what, on the left here is a steady geotherm, where you see that there's essentially a ductile ice that is essentially close to the melting point. And then there's, due to the low temperature dependence of the thermal conductivity of ice, you get a very thick conductive lid. And if you want to even just, increase the convecting ice up to where the salts are, you need a very large perturbation, right? And that's has to come from one of these effects that I've mentioned. But so if we assume for now that we somehow have near surface melting and that the oxidants are mixed into the brine, then we are now in the situation where I can start to help think about this. And the questions in terms of oxidant transport are two. Well, one is the ice permeable, right? Because if it's not permeable, well, then you can't percolate. And then the second is there's a competition between assuming that whatever forms the chaos terrain is a transient event, right? So whatever that extra heating is goes away, then there's a competition between refreezing the brine that's formed near the surface and it draining. And then the third thing, so that's competition of two different processes. And the third thing is the brine needs to actually transport the oxidants, and that is not trivially clear because these porosity waves typically are not thought to transport oxidants. So let's think about whether the ice shell is permeable or not. And clearly I haven't had time to put in the right slide, but Brittany Schmidt had a very influential paper where she clearly assumes that the ice underneath the brine is not permeable. So here's a standard ice shell convection model. So you see the conductive lid, it's very thick. Black are the streamlines, and the color is the temperature. And here we've shaded in this red here, all the areas where the temperature here has actually exceeded the melting point of pure ice, okay? And the reason this happens is that ice shell convection is internally heated, right? So there's tidal dissipation that increases with the temperature that is highest somewhere near the melting point of ice. And so in that lower region, we have huge amounts of tidal dissipation that is essentially like a source term on the energy equation. And what this leads to in these convection models is that you actually raise the temperature, in the numerical model, you raise the temperature above the melting point of ice. And what everybody else does, you just saturate your color scheme and just move on. But this clearly shows that with what we think are reasonable amounts of tidal dissipation, actually a good part of the lower ice shell is, in this case, modeled as above the melting point. But what that would really mean, of course, is there would be partial melting occurring here. And of course, where this, here in the middle is a cold downwelling, but in the hot upwelling, essentially the entire ice shell is in a state of sort of latent melting. And of course, if we're going to form a chaos terrain, it's going to be above some upwelling. So I personally believe that in the ductile ice, and this is without the presence of any salts, right? If you add salts to this, the entire thing would be probably partially molten. So I think now an interesting question is what happens to these melts, and we don't know, but certainly there's a good argument that can be made that there is partial melting occurring, and so there's some porosity that's filled with this partial melt. And now the question that seemed the really contentious one when we started in this in 2017-18 was whether this partial melt, it's not going to be 30% partial melting, right, or 50 or something huge, but it's going to be 1, 2, 3, maybe 10. So it's going to be a small amount of small degree partial melt. Whether this partial melt would be connected so that it can flow, or whether it would sort of sit in isolated little blobs. And this is, so here is a graph of porosity or melt fraction on the bottom, and K here is the permeability. So that's a measure for how easy it is for pore fluid to flow through a porous medium. Here are some estimates of, potential melt fractions due to different salts that you could have. So in the ductile ice shell, so this was before I realized that the whole thing melts even without any salts present. So this is an old graph. But so the only data that we have on ice permeability comes from a bunch of work on sea ice. And what you see here is that it's all at porosities bigger than 5%. And in fact, people have studied this, have suggested that here's a very early CT scan. So nowadays this would look much sexier, but this in sea ice, the brine is left behind in these little isolated bubbles. And there's the suggestion that in sea ice, there's a percolation threshold that means at porosities less than 5%, essentially there's no permeability, right? And if that is the case, then even though you may have partial melting in the ice, you wouldn't transport the brine because it's not permeable, it can't flow, it can only move with the ice itself. Now, interestingly enough, so that's one view of the permeability of ice that's based on brine pockets in sea ice. Right? Interestingly enough, there's another point of view of brine distribution and permeability in ice, and that comes from people that do partial melting experiments. So if you, and this is an amazing, it's one of my favorite scientific images here on the right. This is by Rempel et al. And actually this is a Nature paper, but he's actually taking it from somebody else who I believe is called Mather. This is an optical microscope image of a water channel on the grain boundaries of like 4 ice grains that are next to each other. So there's what we call a triple junction or something like this. So there's a tetrahedral junction here where 4 grains come together. And then these channels that go off to the side is a grain edge where 3 grains come together. And you can show that because the water wets the ice grain boundaries, these networks essentially do not have a percolation threshold. And so you can show that these, within the limit of the continuum theory applying, there is no percolation threshold. And so we have these 2 very opposing views on the permeability of brine or water within ice, where one assumes essentially that we have these isolated blobs at low porosities, and the other ones assume we have these sort of perfectly connected grain edge networks. And the reason is that these are 2 different, they're formed by different processes. So the sea ice is a solidification texture, while this is really a partial melting texture. So you take a solid that's polycrystalline, you raise it above the melting point, and then it begins to form these. The solidification texture, is a classical example of something that happens very far from equilibrium. You form spiky crystals and so on and so forth. While this here is, well, what just happened? It's clearly near equilibrium. And so, in my opinion, is that this kind of isolated blobs, you may get this near the ice-ocean interface where you're actually freezing the ocean to make ice. But once you're inside a, solid state convecting ice shell, you're going to have very nice recrystallized ice texture, and you're actually undergoing partial melting. So I think this is the relevant texture. But of course, we'll not know. And if that is the case, then if the ice shell is essentially partially molten, it would mean that it's also permeable, right? And then comes the dynamic question of whether the brine can essentially drain faster than it's refreezing. And so for this, we built a numerical model for oxidant delivery. And I haven't had time to punch in the equations, but we're building on a melt migration model that Jake Jordan, my former PhD student, built. And here you can actually see a porosity wave in 2D. So the golden lines here, that's the porosity contour. So we have a two-dimensional porosity wave. And you can actually see that in 2D, you get these nice recirculating flows inside the porosity wave. Anyway, so we have a code that does that. And then for this paper, we wrote this phase behavior model, which allows us to run, so this is a 2D calculations with many, many time steps. At every time step in every cell, you need to evaluate the phase behavior. If you call some external package, you'll never finish. And we've essentially boiled it down to something that we can evaluate analytically. So we can do 1 million of those in 6 seconds. And so the phase behavior is not slowing us down. And then we also need a transport solver, which actually is harder than it sounds because it's a multi-phase system. But we've done that. And so now, because we don't really know how chaos terrains form, okay, my tendency is to start with a simple initial, rather than trying to make some fake chaos terrain looking thing up here, my tendency is to just do something very simple. And so our assumption here is that we have a background ice shell that has a very low melt fraction, okay? That's because of the tidal heating and because of small amounts of salt that always get entrained in the salt. And then we have a region at the top where there's more salt, and that increases the melt fraction, actually much lower. People suggest up to 30%. We're here at 1%. This has multiple regions, partially because, of course, in an actual chaos terrain, you have fully solid blocks, probably next to things that are 30% molten. So here we've homogenized that. But there's also the limitation that our code is in the limit of small melt fraction. So if the physics will go haywire if we make the melt fraction too big. But clearly, anyway, this is certainly in some sense a conservative case. And then we assume that the tracer essentially has been mixed into this. And that's our initial condition. And now the question is, can this brine drain fast enough, or does it just refreeze near the top? And first, so here's a 1D simulation from some abstract some time ago. And so we assume essentially a constant initial temperature. So we assume that some perturbation has simply brought the convecting temperature all the way to the surface. And that's, of course, a dramatic simplification, but we simply don't know what else to start with. And what you can see here is some sort of error function type of profile, of course, propagating back into the ice, freezing it, the surface being at 100 K. And here you see the initial condition in the porosity. So we have this region near the surface that has an increased porosity. And then the porosity of the underlying ice is so low that you don't see it, but it's not impermeable. And then what you see happens here is that in this region here at the top, the melt runs down quickly and piles up at the bottom of the region of increased partial melting. But then it actually begins to dilate the ice underneath, and eventually the ice opens up, and then you get these porosity waves migrating down, very similar to what Clark Kalsova showed. This plot here shows the volume fraction of salt that's been precipitated. So you see at the very top, we actually precipitate some salts, but then we stop because actually the brine migrating down takes all the salt with it and is essentially drained from the ice shell. And here on the left, you see the oxidants moving, and you can see that actually even in 1D, the porosity wave does take the oxidant with it. And that's just because the transport distance here is relatively short. And then so this is 1D, right? But it turns out that the amount of tracer or geochemical constituent that you transport depends drastically on the dimension of this porosity wave. And so to get a better handle on this, we did sort of a pseudo 3D calculation where we assume a cylindrical coordinate frame. So it's actually 2D, but the volumetrics and for that matter, the dynamics are similar to 3D. It's the same idea. We have an ice shell of about 25 kilometers. So the blue and red here is the normalized oxidant concentration. And you can see that I've massively saturated it here just to help you, to help visualize the pattern, really. And in white, we have porosity contours. And so you see, initially you form this sort of very high porosity layer against the base of the initially partially molten region. So that those are those horizontal white lines. And then the oxidant in red begins to leak into the underlying ice, and then eventually a porosity wave forms, establishes itself, propagates down with a constant phase velocity. And then you see that the oxidant is caught in this sort of swirl within this porosity wave. And this is just here, just shows you that. So to visualize those streamlines, you go in a Lagrangian reference frame that moves with the phase velocity, and then you can see that you have recirculating streamlines in this porosity wave. And that's what effectively transports the oxidants. And in this calculation, we see that in about 20,000 years, we've delivered 80% or something like that of the oxidants downward. And so purely from the brine drainage dynamics, we can conclude that due to all the tidal heating, the presence of salts, there's a good reason to believe that the ice shell is permeable. And clearly the brine drains faster than the refreezing, so that's what our simulations show. And it also shows that the oxidants are being transported. Now, one thing, maybe just this image here is, this is only 3 kilometers radial. These chaos terrains can be thousands of kilometers across. So don't imagine a single one of those forming, but sort of more of a, many of these mushrooms growing downward from underneath one of these terrains. So from a pure brine dynamics point of view, the oxidant delivery is certainly possible. Right, and then of course, if we take, with all the caveats that we've put in place, if we take our numbers at face value, and we have estimate of the surface O2, we can look at the fraction of the area that is labeled chaos terrain, fraction that's delivered, that means surface age, and then we can estimate ocean delivery rates at current time, or however, in the last 100 million years, which are represented by the surface apparently, somewhere between 10 to the 6 to 10 to the 10 moles per year. And this is by definition, of course, lower than previous estimates, because previous estimates just assume the entire ice shelf turns over. And of course, we only deliver a part of the oxidants to the surface. So you can see here, previous estimates are somewhat higher. So just in summary, so we looked at oxidant transport by brine drainage, and certainly early on in all of this, the argument of ice permeability seemed to be prevalent. More recently, it seems that people are more accepting of having a permeable ice. We've looked at the sort of brine drainage dynamics, and certainly if the oxidants do get mixed into these near-surface brines, can drain and can transport these oxidants before the brines refreeze near the cold surface. And then if you kind of try to do the numbers, you can estimate the surface oxygen abundance, and then you can come up with rates. And the question then is always, is this sufficient for life? And then I always punt to Steve Vance, but so with this, I think we're done. How are we doing for time here? Okay, perfect. And so I'll leave it here.
Thank you.
Thanks, Mark. That's great.
We can open up for questions. Probably just unmute yourself and go for it.
Hey, Mark, what would the role of ice shelf thickness play in all this?
Who's Eric?
Because I know there's a ton of estimates between what's the thickness.
I'm still trying to get the balance right between actual science and just blah blah. So what determines is not the actual ice shell thickness, right? But it's the physics here there's an internal length scale called the compaction length, okay? And that is the length over which you can communicate a pressure gradient in this soft, slushy, ductile ice. And so what really matters is how many compaction length is the ice shell thick. And the small, if you assume that the ice shell is somewhere between kilometers to tens of kilometers, so 1 order of magnitude, but so that definitely goes in there. But for example, the viscosity of ice could vary by like 3 or 4 orders of magnitude, right? similar with the permeability, depending what you depend. So the actual ice shell thickness is, unless it's extremely thin or extremely thick, is less of a matter in determining this, but it's really the unknown viscosity, and it's the viscosity of this. Viscosity of ice, itself is maybe easier, but it still depends on grain size. But once you have a partially molten ice or ice that has little salt crystals in it, then our estimates of the viscosity are a lot more hairy, and so that's what makes it. But essentially, if we had ice shells, so right now, so everything here is actually, so for the calculations that I'm doing, the compaction length is about 1 kilometer. It's 900 meters. If the ice shell is less than if the compaction length is larger than the ice shell thickness, then you can't localize the melt flow, and then essentially the entire ice, it's almost like a 1D model. It just has to, the porosity just generally increases, and then the melt goes down, and then the porosity generally decreases, and it tends to go much slower. And in that case, maybe you would freeze more of the melt. Now, if you have a very weak ice, so the compaction length is, say, only a few meters or something like that, tens of meters, then it would look like that, but the size of the porosity waves, the speed, and so on, the maximum porosity, those would all change. I think
go
probably had his hand up for the longest.
Let's
see.
Yeah, I had a question about the first part of the process, the oxidant production. So impact gardening is needed to mix the regolith, but does that not liberate the oxidant from, like, as it's being churned? Why isn't the oxidant liberated?
Yes, so we this is where Provo Oza would be the person to to respond to this, but we did find a reference from probably Johnson or somebody like this that said that these oxygen bubbles are believed to be stable on orbital timescales. Yes, I mean, well, let me phrase it this way. So it's sort of interesting, right? So it's trying to think of bubbles, and I'm like, what do you mean by bubble? But I mean, clearly, the grain that the micrometeorite hits probably gets vaporized or melted or whatever, right? And whatever oxygen was there, that's directly affected by the impact probably gets released. But I think it stirs, my understanding, the way this is supposed to work is that it stirs this granular medium over, over a larger volume, if that is any consolation. So it is not my expertise, but in general, people seem to believe that these oxygen bubbles, well, I guess you could just argue the following. Well, you could say, would they be, I mean, we're measuring the we're not, they are measuring the oxidants. So they are present, but I guess the question is how deep, right? Yeah, but the general assumption seems to be that it survives the impact gardening.
So Marc, so one quick question. In your simulations, you used 1% porosity as the porosity in the melted region. So if we increase the porosity, then the melt migration will be much faster. Right?
Well, it depends, right? It's the porosity down here that's limiting, right? What happens if I increase this to 5-10%, then what will happen is this already is grown here to 60% porosity. This will just grow towards 1, and I'm just and and the equations only work for in the limit of phi equals small. So I mean, it's essentially what happens here, right? Essentially, you float the ice on the top and you form just a lake, right? That's what's happening. Now the dynamics in that lake, I'm not. Well, they may actually be interesting. I don't want to say anything, but that doesn't come to. As long as we communicate the pressure to the bottom of the ice, is that your pigeon? So yeah, it just so that's how we're working on a non. Well, truth be told, right? Essentially, you have to switch to just anyway. So we're just trying to avoid having extremely large porosities, but yeah, it should. it certainly helps. More melt helps this process.
Interesting. And the melt that you have initialized, it was, I think, 0.1%. Is it like a conservative estimate, or is it something you're using from the constraints or bounds that you have?
So the only one who's ever been bold enough to try and estimate the amount of partial melting there is Brittany Schmidt, and I'm trying to remember her argument, but she certainly came up with things as high as 30%, right? But when you think of this, when you think of these images here, these ones, essentially you have regions, right, where there's no porosity, right? And then you have, I mean, that's, so, okay, so personally, I think it's got to be something like this, right? So some upwelling and then partial melting on top of that. So so you have regions of essentially no melting, and then you have sort of, and the way I imagine it, that Brittany thinks that there's in here is maybe up to 30% or maybe even more, but then here you'd have none. So if you just, and so the way we justify the lower porosity initial condition is to just say, well, we're just averaging over this. I played with the thought of trying to come up with, with something that looks like this, but then, I feel like sometimes if you don't know, it's better to be simple, but.
Makes sense. Thank you, Mark.
I see Natalie entered something into the chat. I'll read it for her unless she wants to.
I can, yeah, go ahead. So I guess my question is like, what's the significance of like the porosity waves themselves? Like intuitively, to think about this problem, it seems like if the ice shell is permeable, it's going to drain and retain some fraction of oxidants.
Right. So I guess where is it? So maybe you can think about it here. So the porosity waves do move much faster than the back. So here, this is the classic example. So the black here is the porosity, right? And the background looks like there's no porosity, but there is. Actually, nobody knows what happens to this if there's no background porosity. But for this model to work, there needs to be a very small background porosity. And if you just look at the Darcy flow velocity due to buoyancy in that background velocity, it's that dashed line. That's how fast things would move through that background porosity, right? So the I guess dynamical significance of the porosity wave is that it moves, whatever, an order of magnitude or so faster than the actual melt. So and that helps get the melt away from the cold surface. Does that go?
That was, yeah, exactly it. Thanks, Mark.
That's great.
Okay. Unless there is something else pressing, let's thank Mark, and we will see him at the next meeting of the group.
Yes.
Thanks, Mark. That was great.
Thanks.
Bye, guys. Bye, everybody.
So Mark, do you have a comment on, I started recording this a few minutes late.
No, yeah, I have no comment. You can, I guess you guys make